NOAA just confirmed something that space weather trackers have been watching develop for days. 2 separate blasts of solar material are hitting Earth within a single 24-hour window. The first wave has already arrived. The second is coming within hours, and when 2 solar storms strike back to back like this, Earth's magnetic shield doesn't respond the way it does to a single impact. The effects compound. The interactions amplify. Scientists are watching what happens next very carefully. But before you worry, this is not a danger to you personally. What makes this fascinating isn't fear, it's rarity. It's the science of what occurs when our planet gets hit twice before it can fully recover from the first blow. This doesn't happen often. The timing has to align perfectly, the source has to be powerful enough, and the trajectory has to be precise. All 3 conditions just lined up. If you're watching this right now, you're witnessing something that most people won't even notice happening around them. Their phones will work, the lights will stay on, life continues exactly as it did yesterday. But above us, in the invisible space between Earth and the Sun, something remarkable is unfolding. Our planet's magnetic field is being struck by forces that travelled millions of miles across empty space, carrying energy that was unleashed from a single active region on the Sun's surface. This isn't science fiction. This is science fact. And it's happening right now, while you're sitting wherever you are, reading these words, living your normal day. Stay with me for the next few minutes because we're going to walk through exactly what's happening, why it matters, what makes this particular event so scientifically noteworthy, and what you can actually expect over the next day or 2. No hype, no fear-mongering. Just the real story of a double solar strike that scientists find genuinely interesting, explained in a way that makes sense. Here's what you need to understand from the start. When people hear solar storm, their minds often jump to disaster scenarios. Blackouts, satellite failures. Technology is collapsing, and that's definitely not what we're dealing with here. What we're experiencing is a moderate-level event that happens to have an unusual characteristic: the timing. 2 coronal mass ejections, both launched from the same region of the Sun, arriving at Earth within the same day. That's the part that catches attention, not because it's catastrophic, but because it's uncommon. It's the kind of event that makes space weather scientists lean forward in their chairs and say, "Okay, let's watch this closely and see what happens." The official confirmation came from NOAA's Space Weather Prediction Center. They issued a G2 Geomagnetic storm watch for the first impact, followed by a G1 watch for the second. If you don't know what those numbers mean yet, don't worry, we'll get there. What matters right now is understanding that these are manageable, well-understood events. We have protocols, we have monitoring systems, we have decades of experience handling situations exactly like this. The difference today is simply that we're getting 2 punches instead of 1, and they're coming so close together that Earth's magnetic field won't have fully reset from the first before the second arrives. Think about it this way. Your body has systems that respond to stress. If you get startled once, your heart rate spikes, then settles. But if you get startled twice in rapid succession, that second spike builds on the first. Your body hasn't fully calmed down yet. Earth's magnetosphere works similarly. It can absorb and deflect solar wind and plasma. It's been doing that for billions of years. But when 2 significant bursts come in quick succession, the response amplifies. Not dangerously, not catastrophically, but measurably. And that's what makes this worth understanding. So what actually happens during an event like this? Satellites in certain orbits experience slightly elevated radiation exposure. GPS signals might lose a bit of precision for a few hours. Radio communications at high latitudes could get choppy. Power grids in northern regions see voltage fluctuations that operators monitor and manage routinely. And if you're lucky enough to be in the right place at the right time, you might see auroras dancing across the sky far south of where they normally appear. That's the reality. Manageable impacts, monitored systems, and a spectacular light show for those positioned to see it. But here's the part that should genuinely capture your curiosity. This double strike didn't come from random solar activity scattered across the Sun's surface. Both eruptions originated from the exact same active region, the same sunspot cluster, the same magnetic complexity that we've been tracking as it rotates across the face of the Sun. That region is designated AR4324, and over the past several days it has proven to be remarkably productive. It fired off 1 significant eruption, sending a coronal mass ejection toward Earth. Then, roughly a day later, it fired again. And because the Sun rotates, because Earth moves in its orbit, and because the physics of solar eruptions follow predictable patterns. Both of those ejections are now converging on our planet within the same narrow time window. You're not going to feel this. You won't see your lights flicker unless you're in a very specific location experiencing a very specific set of conditions. Your phone will charge normally. Your internet will stream. Your car will start. The vast majority of human activity on Earth will proceed exactly as it does every other day. But above the atmosphere, in the realm of satellites and space-based infrastructure, systems are being stressed in ways that engineers anticipated and prepared for. And in the magnetosphere, that invisible shield that surrounds our planet, particles are colliding, energy is being transferred, and the auroral zones are lighting up with colours that people will photograph and share and remember. This is what space weather looks like when it intersects with modern civilization. It's not the end of the world. It's not even a significant disruption. But it is a reminder that we live on a planet orbiting a star, and that star is active, dynamic, and constantly influencing the environment around us. We've built our technology to be resilient. We've designed our infrastructure to handle these events. And we've developed the scientific understanding to monitor, predict, and respond appropriately. Now, before we go deeper into the science, the history, and what you can actually watch for over the next day, I want you to do something. If you find this kind of content valuable, if you want to stay informed about space weather events as they develop, hit that subscribe button right now. This isn't the last solar storm we'll see this year. We're in an active phase of the solar cycle, and events like this are going to continue happening with increasing frequency over the next couple of years. By subscribing, you're making sure you don't miss the next one, and drop a comment below telling me where you're watching from, because I'm genuinely curious how far this information reaches and whether you're in one of the zones where auroras might be visible tonight. This is happening in real time, and you're part of the story just by paying attention. So let's dive in. Let's talk about how this event developed, why scientists predicted it, and what the next 24 hours are going to look like as Earth navigates through this double wave of solar material. If you watched my video yesterday, you know I talked about exactly this scenario. I explained that AR4324 was showing signs of significant magnetic complexity. I walked through the possibility that this active region could produce multiple eruptions in close succession. I used the term black swan event not because I was predicting disaster or danger, but because I was highlighting the rarity of a double strike scenario where both impacts arrive at Earth within the same narrow time window, and within 24 hours of posting that analysis it happened. Both eruptions occurred, both coronal mass ejections launched toward Earth, and now, as you're watching this, both are arriving. This isn't about me being right. This is about the science working exactly as it should. Space weather prediction has advanced dramatically over the past 2 decades. We have satellites positioned between Earth and the Sun specifically to give us early warning. We have ground-based observatories monitoring the Sun's surface continuously. We have models that take solar wind data and project when and where coronal mass ejections will arrive. None of this is guesswork anymore. It's measurement, calculation, and pattern recognition built on decades of observation. Let me walk you through the timeline so you understand how this unfolded. On December 31st, AR4324 produced a significant solar flare. It registered as a McClass flare, which means it was moderate in strength but still energetic enough to launch material away from the Sun. That eruption sent a coronal mass ejection toward Earth. Space weather forecasters immediately began analysing the trajectory and speed. They determined that this CME would arrive at Earth around midday on January 3rd. That was the first impact, the one that already hit. Then, roughly 24 hours after that first eruption, AR4324 flared again. This time it was a slightly weaker event, but still significant enough to produce another coronal mass ejection. The second CME was trailing behind the first, moving through space along a similar path. And because of the timing, because of the speeds involved, forecasters calculated that the second CME would arrive at Earth just hours after the first. Not days later, not a week later, hours. That's what creates the compounding effect. That's what makes this noteworthy. NOAA's Space Weather Prediction Center issued their first alert on January 2nd. They posted a G2 Geomagnetic storm watch, indicating that moderate storming was possible when the first CME arrived. Then, as data refined and the second eruption became clear, they issued a secondary watch for G1 conditions extending into the following day. If you've been following space weather coverage from other sources, you probably saw spaceweather.com post an update confirming that a pair of CMEs was heading toward Earth. They used almost the exact same language. A pair of CMEs. That phrasing matters, because it signals something beyond the routine. Now let's be very clear about what a prediction like this actually means. Forecasting the arrival time of a coronal mass ejection is not like forecasting the weather on Earth, where you can track a storm system moving across the continent with radar. Coronal mass ejections travel through the vacuum of space, and their speed can vary depending on the solar wind environment they're moving through. Early projections are based on initial velocity measurements taken by satellites near the Sun. As the CME travels closer to Earth, instruments positioned at the L1 point, roughly 1 million miles upstream from our planet, provide refined data. That's when forecasters can say with high confidence, impact will occur within the next 6 to 12 hours. That's where we are right now. The first CME arrived earlier today. If you check NOAA's real-time magnetometer data, you'll see the signature. There's a clear disturbance in Earth's magnetic field that began during the expected window. The second CME is on its way, and its arrival is anticipated within the next several hours. By the time most people watch this video, both impacts will have occurred. But if you're watching this early, you're seeing it unfold in real time. You're watching the prediction become reality. This is why I keep coming back to the term black swan in the context of space weather. Not because these events are completely unprecedented, but because they represent the convergence of multiple low-probability factors. Active region complexity, multiple eruptions from the same source, precise timing that places both CMEs at Earth within the same day, Earth-directed trajectories for both ejections. Any one of these factors is common. Having all of them align simultaneously is not. That's what we're witnessing. That's what makes this scientifically interesting. I want you to understand something important here. When scientists say an event is noteworthy or unusual, they're not speaking in code for dangerous. They mean exactly what they say. This is worth noting. This is outside the routine. This is an opportunity to observe, measure, and learn. Space weather science advances by studying events that deviate from the average. Single CME impacts are well understood. We've seen thousands of them. But double impacts with tight timing, those are rarer. They provide data that helps refine models and improve future predictions. And here's the part that should give you confidence in the entire system. The prediction worked. We saw the eruptions on the Sun. We tracked the CMEs as they traveled through space. We calculated their arrival times. We issued watches and warnings to the appropriate operators and agencies. And now, the impacts are occurring exactly as forecasted. This is not luck. This is applied science functioning as designed. It's the result of billions of dollars invested in satellite networks, ground observatories, computational models, and trained personnel who monitor space weather around the clock. So when you see headlines that say, NOAA confirms double solar strike, understand that the confirmation isn't surprising. It's validation. It's the system working. It's the difference between being caught off guard by a space weather event and being fully prepared with days of advance notice. We chose preparation, we built the infrastructure, and it's delivering exactly the information we need, exactly when we need it. But knowing that an event is happening and understanding what it actually means are two different things. The headlines will tell you that 2 CMEs are hitting Earth. They won't always tell you what that really looks like, what the physical process involves, or why the timing creates the compounding effect that scientists find so interesting. That's what we need to unpack next. Because to truly appreciate what's happening right now, you need to understand the basic mechanics of how Earth interacts with solar storms. You need to know what a coronal mass ejection actually is, what Earth's magnetosphere does, and what changes when you get hit twice instead of once. That's where we're going now. That's the foundation that turns this from a headline into genuine understanding. And once you have that foundation, everything else, all the effects, all the implications, all the historical context, it all clicks into place. Let's start with the basics, because if you don't understand what a geomagnetic storm actually is, the rest of this won't make sense. And I don't mean a textbook definition. I mean a real, practical explanation of what happens when the Sun throws material toward Earth, and that material interacts with our planet's magnetic field. This isn't abstract physics. This is observable, measurable, and happening right now above your head. The Sun is not a solid ball of rock like Earth. It's a massive sphere of superheated plasma, where hydrogen atoms are being crushed together by gravity so intensely that they fuse into helium, releasing enormous amounts of energy. That energy radiates outward as light and heat, which is why we have sunlight, why plants grow, why life exists. But energy isn't the only thing the sun releases. It also constantly emits a stream of charged particles, electrons and protons, that flow outward in all directions. We call this the solar wind. It's always there. It never stops. And Earth sits in that flow like a rock in a river. Now, most of the time, the solar wind is relatively steady. It fluctuates, but within predictable ranges. Earth's magnetic field acts as a shield, deflecting the majority of those particles around the planet. This is why we're not constantly bombarded by radiation from space. Our magnetosphere, that invisible bubble of magnetic influence surrounding Earth, does the job it's been doing for billions of years. It channels particles away, funneling some of them toward the polar regions where they interact with the upper atmosphere and create auroras. That's the baseline. That's normal space weather. But sometimes, the sun does something more dramatic. Deep within its structure, magnetic field lines become twisted and tangled. When those magnetic tensions become too great, they snap. And when they snap, they release energy in the form of a solar flare, a sudden burst of light and radiation. Often, that magnetic restructuring also hurls a massive cloud of plasma away from the sun's surface. That cloud, that billion-ton bubble of charged particles and embedded magnetic fields, is a coronal mass ejection, a CME. And if that cloud happens to be aimed toward Earth, it becomes our concern. A coronal mass ejection doesn't travel at the speed of light. It's physical matter, plasma and magnetic fields, moving through space. Depending on its initial velocity, it can take anywhere from a day to several days to cover the distance between the Sun and Earth. During that journey, it's expanding, cooling, and interacting with the ambient solar wind. When it finally reaches Earth, it slams into our magnetosphere like a wave hitting a breakwater, and that's when a geomagnetic storm begins. The strength of the resulting storm depends on several factors. How fast was the CME travelling when it arrived? How dense was the plasma? What was the orientation of the magnetic field embedded in that plasma? That last one is critical, because if the CME's magnetic field is oriented opposite to Earth's magnetic field, they connect, they couple. And when that happens, energy transfers from the CME into Earth's magnetosphere much more efficiently. The magnetosphere compresses, particles are injected into regions where they don't normally reach. Currents start flowing in the upper atmosphere and along the surface. And all of those changes, all of that energy transfer, that's what we measure as a geomagnetic storm. Scientists use a scale to categorize these storms. It's called the scale, and it runs from G1 to G5. Think of it like the Richter scale for earthquakes or the Saffir-Simpson scale for hurricanes. It's a way of quickly communicating intensity. A G1 storm is minor. You might see auroras slightly farther south than usual. Some satellites might experience minor operational anomalies, that's about it. A G2 storm, which is what we're dealing with today, is moderate. Auroras become visible at mid-latitudes. Satellites in certain orbits need to account for increased drag from a slightly expanded atmosphere. Power grids at high latitudes might see some voltage irregularities that operators monitor and correct. Still manageable, still routine for anyone who works in these fields. Then you have G3, strong storms. These are less common, maybe a couple dozen per solar cycle. G4, severe storms, happen a few times per cycle and can cause more significant issues for satellite operations and power grids. And G5, extreme storms, are the ones that make history. The Halloween storms in 2003, the Quebec blackout in 1989, those were G5 events. They're rare, they cause measurable damage, and they require significant response efforts. What we're experiencing right now is a G2 storm, possibly briefly reaching G3 conditions depending on how the magnetic fields align when the second CME arrives. This is not a G5. This is not a historic event in terms of intensity. What makes it unusual is the double impact, not the severity. And that's an important distinction because the intensity determines the effects, but the timing determines how those effects might amplify. So what does a G2 storm actually do? Let's get specific. Satellites in geosynchronous orbit, the ones that handle communications and weather monitoring, sit about 22,000 miles above Earth's equator. Normally they're well within the protective bubble of Earth's magnetosphere, but during a geomagnetic storm that magnetosphere compresses, the boundary gets pushed inward. Satellites that are normally safe can suddenly find themselves on the edge of that boundary, exposed to higher levels of radiation. This doesn't destroy the satellite, it doesn't knock it offline, but it increases the wear on sensitive components and raises the probability of temporary anomalies. That's why satellite operators pay attention to space weather forecasts. They can put satellites into safe modes if necessary, reducing activity until conditions settle. GPS accuracy can degrade during geomagnetic storms because the signals from GPS satellites travel through the ionosphere, the layer of Earth's atmosphere between about 50 and 600 miles altitude. During a storm, the ionosphere becomes more turbulent. Electron density fluctuates, and those fluctuations cause GPS signals to refract slightly, introducing errors. For most consumer applications, you won't notice. Your phone's map app will still get you where you're going, but for high-precision applications, surveying, aviation, autonomous vehicles, that degradation matters. And again, this is known. It's accounted for. Systems are designed to recognize when ionospheric conditions are poor and adjust accordingly. Power grids, particularly those at high latitudes, can experience something called geomagnetically induced currents. During a storm, rapid changes in Earth's magnetic field induce electric currents in long conductors, like power transmission lines. These currents can cause transformers to overheat or saturate, reducing their efficiency. Grid operators monitor this in real time. They can adjust load distribution, bring backup systems online, or temporarily reduce transmission through affected lines. It's not a blackout scenario unless the storm is severe and the response is inadequate. For a G2 storm, it's routine monitoring and minor adjustments. Radio communications at high frequencies, the kind used by aircraft flying polar routes or by amateur radio operators, can be disrupted because those signals bounce off the ionosphere. When the ionosphere is disturbed, signals get absorbed or scattered instead of reflected. Again, this is temporary. It lasts as long as the storm persists, then conditions return to normal. And then there are the auroras. This is the part most people find beautiful, rather than concerning. When charged particles from the CME are funneled along Earth's magnetic field lines toward the poles, they collide with oxygen and nitrogen molecules in the upper atmosphere. Those collisions excite the atoms, and when the atoms relax, they emit light. Green from oxygen at lower altitudes, red from oxygen at higher altitudes, purples and blues from nitrogen. During a G2 storm, the auroral oval expands. People in northern states, places like Montana, North Dakota, Minnesota, Michigan, even occasionally as far south as Iowa or Pennsylvania, might see the glow on the northern horizon. It's not dangerous. It's not a warning sign. It's just physics producing something visually stunning. That's what a geomagnetic storm is. That's what the G-scale measures, and that's what we're experiencing right now. Managed effects, monitored systems, and a light show for those positioned to see it. But remember, we're not dealing with a single storm. We're dealing with two CMEs arriving in rapid succession. And that changes the dynamics in ways that scientists find genuinely interesting. That's what we need to explore next. Because understanding the difference between one impact and two, understanding why timing matters so much, that's where the real science of this event comes into focus. Here's where it gets genuinely interesting. Here's why space weather scientists are paying closer attention to this event than they would to a standard single CME impact. It's not about the intensity, it's about the timing, and what happens when you hit a system twice, before it has a chance to fully recover from the first blow. This is the core of why this event qualifies as what I've been calling a black swan scenario, not because it's catastrophic, but because it's a rare convergence of conditions that creates something worth studying carefully. When a single coronal mass ejection hits Earth's magnetosphere, the interaction unfolds in stages. First, there's the initial compression. The CME's magnetic field and plasma pressure push against Earth's magnetic field, compressing it on the day side, the side facing the Sun. That compression can reduce the distance from Earth's surface to the outer boundary of the magnetosphere by thousands of miles. It's like squeezing a balloon. The balloon doesn't pop, but its shape changes dramatically. As the CME continues to flow past Earth, particles are injected into the magnetosphere, particularly if the magnetic fields connect in a way that allows efficient energy transfer. Those particles get trapped and start circulating. Some spiral along magnetic field lines toward the poles, creating auroras. Some get swept into the magnetotail, the elongated part of the magnetosphere that stretches away from the Sun on the night side of Earth. Energy builds up in the magnetotail and eventually it releases in what's called a substorm, a sudden burst of particle injection back toward Earth that intensifies auroras and drives currents in the ionosphere. Then, over the course of several hours to a day or more, the magnetosphere begins to recover. The compression eases as the CME passes. The magnetic field relaxes back toward its normal shape. Trapped particles gradually dissipate or are lost to the atmosphere or to space. Currents diminish. The system returns to its baseline state, ready to handle the next disturbance whenever it arrives. That's the normal cycle. That's what happens with a single impact. The magnetosphere is a dynamic, resilient system. It absorbs the punch, processes the energy, and recovers. This has been happening for billions of years, long before humans existed, long before we had satellites or power grids or GPS. Earth's magnetic field has been protecting the planet through countless solar storms. It's exceptionally good at its job. But now imagine this. The first CME hits. The magnetosphere compresses. Energy starts transferring. Particles are injected. Currents begin flowing. And before that entire process can complete, before the magnetosphere has fully relaxed, a second CME arrives. Not days later. Not even a full day later. Hours later. The second impact arrives while the system is still processing the first, and that's when things get more complex. The second CME doesn't encounter a magnetosphere at rest. It encounters a magnetosphere that's already compressed, already energized, already dealing with enhanced particle populations and elevated current systems. The second compression builds on the first. The second injection of particles adds to populations that haven't yet dissipated. The energy that was starting to release gets interrupted and amplified by new energy arriving from the second CME. This is what scientists mean when they talk about compounding effects. Think of it like this. Imagine you're holding a spring and you compress it with your hand. It pushes back. You can feel the resistance. Now imagine you release the spring halfway, but before it fully extends, you compress it again, harder this time. The spring doesn't just resist the second compression. It resists it more because it never fully recovered from the first one. It's still partially compressed. The cumulative effect is greater than if you had let it fully reset between compressions. Earth's magnetosphere responds similarly. The magnetic field doesn't have time to fully relax. Particle populations that were injected by the first CME are still present when the second CME arrives. The ionosphere is still disturbed, currents are still flowing, and the second impact layers additional disturbances on top of what's already happening. This doesn't mean the effects double, it doesn't mean we get twice the storm intensity, but it does mean that the response can be more complex, more prolonged, and occasionally more intense than a single impact of equivalent strength would produce. This is where the term black swan becomes relevant in the space weather context. A black swan event, in the original sense popularized by Nassim Taleb, is not just a rare event. It's an event that's rare, has significant impact, and is often underestimated or unpredicted because it falls outside normal expectations. In space weather, a double CME impact with tight timing is rare. The probability of two significant eruptions from the same active region, both aimed at Earth, arriving within hours of each other, is low. Not impossible, but low. It requires the right active region, at the right position on the Sun, at the right phase of the solar cycle, producing multiple eruptions with the right timing and trajectories. And here's why it matters scientifically. Most of our models, most of our historical data, most of our operational experience comes from single impact events. We've seen thousands of those. We understand them well. But double impacts with compounding effects, those are rarer. They provide opportunities to test models in conditions that deviate from the norm. They allow scientists to observe how the magnetosphere responds when it doesn't get recovery time between disturbances. They generate data that improves future predictions and helps refine the understanding of magnetospheric dynamics. This is not fear-mongering. This is science. When researchers say they're watching this event carefully, they're not bracing for disaster. They're collecting data. They're measuring parameters. They're comparing observations to model predictions. They're learning. Because every unusual event, every deviation from the routine, teaches us something new about how the Sun-Earth system works. Let me give you a practical example of why this matters. Satellite operators use space weather forecasts to make decisions about when to perform maneuvers, when to upload software, when to conduct maintenance activities. If they know a single G2 storm is coming, they have procedures for that. But if they're dealing with a double impact scenario where conditions might persist longer or fluctuate more unpredictably, they might adjust those procedures. They might delay a planned maneuver by an extra day. They might extend monitoring protocols. It's not panic. It's precaution informed by understanding that double impacts behave differently than single impacts. Similarly, power grid operators at high latitudes know how to handle geomagnetically induced currents from a typical storm. They've done it many times, but if they know the storm environment might be more prolonged or complex due to successive CME impacts, they might keep additional personnel on standby, they might run more frequent diagnostics on transformers, they might prepare contingency plans more thoroughly. Again, it's not because disaster is imminent, it's because the conditions are outside the most common scenarios, and prudent operators prepare for the edges of the envelope, not just the centre. This is what preparedness looks like in the context of space weather. It's not bunkers and survival kits. It's informed decision-making by professionals who understand the systems they're responsible for. It's engineers and scientists who recognise when conditions are routine and when conditions are noteworthy. And it's the public being informed accurately, without hype, so they understand what's happening without unnecessary alarm. Now, you might be wondering, have double impacts like this happened before? Yes, they have, but not frequently. There are documented cases during previous solar cycles where multiple CMEs from the same active region or from different regions arrived at Earth within short timeframes. The Halloween storms in 2003 involved a complex series of eruptions and CME impacts over several days, creating what was essentially a prolonged period of storming with multiple compounding disturbances. That event was far more intense than what we're seeing now, reaching G5 levels, but the principle of compounding effects was absolutely present. The difference between that event and this one is intensity and duration. The Halloween storms were driven by an exceptionally productive active region during a very active phase of the solar cycle. The storms lasted days, not hours. The impacts were severe, not moderate. We're not in that situation right now. What we're experiencing today is a smaller scale version of the same physical process. 2 impacts, tight timing, compounding effects, but at a much more manageable intensity level. And that's actually valuable from a scientific perspective, because it means we can study the phenomenon without dealing with the chaos of a severe storm. Researchers can focus on the dynamics of successive impacts without being overwhelmed by crisis response. It's like studying a moderate earthquake to better understand fault mechanics, which then helps prepare for larger earthquakes in the future. The smaller event teaches lessons that apply when the larger event inevitably occurs. So when you hear scientists say this double impact is noteworthy, this is what they mean. They're not worried, they're interested, they're observing, they're learning. And the data collected from this event will inform space weather forecasting for years to come. It will refine models, it will improve predictions, it will help operators make better decisions the next time a similar scenario develops. But understanding the science is only part of the picture. You also need to understand what this actually means for the world around you right now. What are the real-world effects? Who needs to pay attention? What should you be watching for? That's where we turn next, because knowing the theory is valuable. But knowing how it translates into practical reality is what makes this information actionable. Let's bring this down to ground level. Let's talk about what this double CME impact actually means for the systems and infrastructure you interact with every day. Because that's the question most people have when they hear about a geomagnetic storm. Okay, but what does this mean for me? Is my phone going to work? Will the power go out? Should I be worried? The short answer is no, you should not be worried, but you should understand what's happening and who is paying attention, because that context matters. First, let's talk about satellites. There are thousands of active satellites in orbit around Earth right now, serving everything from communications to navigation, to weather monitoring, to national security. These satellites exist in different orbital regimes, and not all of them are equally affected by geomagnetic storms. Satellites in low Earth orbit, typically below about 1,000 miles altitude, are largely protected by the bulk of Earth's magnetosphere. Satellites in medium Earth orbit, where GPS satellites live, around 12,000 miles up, experience more exposure, and satellites in geosynchronous orbit, sitting at 22,000 miles altitude, are on the frontier of the magnetosphere's protective influence. During a G2 storm, satellites in higher orbits face increased radiation exposure. This comes from energetic particles that penetrate deeper into the magnetosphere than they normally would. The satellites are designed with shielding and fault-tolerant systems to handle this, but the risk of temporary anomalies increases. An anomaly might be a single event upset, where a charged particle strikes a memory chip and flips a bit, causing a brief error that the satellite's onboard systems correct automatically. It might be a sensor giving a spurious reading. It might be increased drag on the satellite's orbit due to atmospheric expansion, requiring a minor adjustment. Satellite operators monitor space weather forecasts closely. When they see a G2 storm predicted, especially one with an unusual profile like a double impact, they take precautions. They might postpone non-essential operations. They might avoid conducting software updates or reconfigurations during the storm period. They might increase the frequency of telemetry checks. These are routine protocols, not emergency measures. This is just good operational practice when the space environment is more dynamic than usual. For you, the end user, this mostly translates to nothing you'll notice. Your satellite TV continues working. Your satellite internet functions. The weather satellite images on the news are still there. The GPS navigation in your car still guides you to your destination. But behind the scenes, engineers are monitoring, adjusting, and ensuring that temporary anomalies don't cascade into larger issues. It's invisible infrastructure management that keeps your experience seamless, even when the space environment is turbulent. Now let's talk about GPS specifically, because this is something people ask about frequently. GPS works by receiving signals from multiple satellites simultaneously and using the time delays between those signals to calculate your position. Those signals travel through the ionosphere, and as I mentioned earlier, geomagnetic storms disturb the ionosphere. Electron density becomes more variable, the ionosphere's height changes, and these variations affect how GPS signals propagate. For most consumer applications, the impact is minimal. Your phone might show your position a few meters off from where it actually is, but the error is small enough that it doesn't matter for navigation. However, for high-precision applications, surveying land boundaries, guiding aircraft during approach, precision agriculture, even some autonomous vehicle systems, that level of error can be significant. Professional users of GPS monitor space weather and can apply corrections or switch to alternative positioning methods when ionospheric conditions are poor. During this double CME event, you might see slightly degraded GPS accuracy for a period of hours, particularly at high latitudes where the effects are strongest. But your phone will still work. Your car's navigation will still get you where you need to go. This isn't a blackout. It's a temporary reduction in precision that professionals account for and consumers rarely notice. Power grids are another area where geomagnetic storms have real-world effects, but again, the effects are managed. At high latitudes, particularly in regions like Canada, Scandinavia, and Alaska, geomagnetically induced currents can flow through power transmission lines during storms. These currents are driven by rapid changes in Earth's magnetic field, which induce electric fields in the ground. Long transmission lines act like antennas, picking up those induced currents. The primary concern is transformers. GICs can cause transformers to saturate, meaning their magnetic cores become overloaded, and they start drawing extra current and heating up. In extreme cases, prolonged exposure to high GIC levels can damage transformers. But grid operators know this. They monitor GIC levels in real time. They have sensors installed at key locations, and when a geomagnetic storm is forecasted, they prepare. Preparation might include adjusting the load distribution across the grid to reduce reliance on vulnerable lines. It might include bringing additional generation capacity online so there's buffer room if adjustments are needed. It might include having repair crews on standby. For a G2 storm like we're experiencing now, these measures are relatively minor. The risk of actual damage is low. The risk of temporary voltage fluctuations is moderate, and those fluctuations are managed through active monitoring and rapid response. For you, sitting in your home, this means nothing changes. Your lights stay on. Your appliances work. You don't experience flickering or outages unless you happen to be in a very specific location, during a very specific set of conditions that would require operators to temporarily shed load. And even that is rare for a G2 storm. The infrastructure is resilient. The people managing it are experienced, and the system functions as designed. Airlines, particularly those flying polar routes, pay attention to space weather for two reasons. First, high-frequency radio communications, which are often used for contact between aircraft and ground control over polar regions where there's no satellite coverage, can be disrupted during geomagnetic storms. Second, Radiation exposure for passengers and crew increases at high altitudes and high latitudes during solar storms. For a G2 storm, airlines might reroute some polar flights to slightly lower latitudes. They might switch to alternative communication frequencies, or they might simply monitor conditions more closely and accept minor communication delays. Again, this is routine operational adjustment. Pilots are trained for this. Dispatchers account for it. Passengers usually have no idea it's even happening. Your flight leaves on time, lands on time, and the only difference is that the route might have been adjusted by a few degrees of latitude, adding a few minutes to the flight time. Radio operators, particularly amateur radio enthusiasts and those who use high-frequency communications for remote operations, will notice effects during a G2 storm. HF radio relies on the ionosphere to reflect signals over long distances. When the ionosphere is disturbed, signal propagation becomes unpredictable. Operators might lose contact on certain frequencies and have to switch to alternatives. Again, this is temporary. It lasts as long as the storm persists, then conditions normalize. And then there are the auroras, which are the most visible and most publicly appreciated effect of a geomagnetic storm. When charged particles from the CMEs are funneled along Earth's magnetic field lines into the atmosphere near the poles, they collide with atmospheric gases and produce light. During a G2 storm, the auroral oval expands southward from the Arctic. People in northern states, places like Montana, North Dakota, Minnesota, Wisconsin, Michigan, and sometimes even farther south, have a chance to see the northern lights. If you're in one of those regions, this is your opportunity. The best time to watch is typically after local midnight, when your location has rotated toward the night side of Earth and the magnetotail is directly overhead. You want to be away from city lights, with a clear view of the northern horizon. The auroras might appear as a faint green glow at first, gradually intensifying into curtains or rays that shift and dance. They might last for minutes or hours. They might be subtle or spectacular. It depends on how the storm evolves and how the magnetic fields align. This is not a danger. This is nature's light show. This is physics made visible. And it's one of the rare instances where a space weather event produces something you can directly observe and appreciate without any equipment beyond your eyes. If you're in the right place, step outside tonight. Look north, and you might witness something extraordinary. So who needs to be paying attention to this double CME event? Satellite operators, GPS professionals, power grid managers at high latitudes, airlines flying polar routes, radio operators, aurora photographers and enthusiasts, and space weather scientists collecting data for research. Who doesn't need to worry? Everyone else. The general public goes about their day exactly as they would any other day. Your routine is unaffected. Your technology works. Your life continues. This is what modern space weather management looks like. It's professionals monitoring and responding. It's infrastructure designed to be resilient. It's the public informed but not alarmed. And it's all of us benefiting from decades of investment in understanding how our planet interacts with the sun. But to fully appreciate how far we've come in managing these events, you need to know the history. You need to understand what geomagnetic storms have done in the past, what we've learned from those experiences, and how today's event compares to historical benchmarks. That's where we turn next, because context shapes perspective, and perspective prevents panic. If you want to understand what's happening today, you need to know what's happened before. Space weather is not a new phenomenon. Geomagnetic storms are not modern inventions. Earth has been bombarded by solar eruptions for as long as the sun has existed. What's changed is our awareness of these events and our dependence on technologies that are vulnerable to them. So let's talk history. Let's talk about the storms that made headlines, the ones that caused real damage, and how they compare to what we're experiencing right now. Because once you understand the scale, once you see where today's event fits in the spectrum of possibility, everything else makes a lot more sense. Let's start with the Carrington event. It's the gold standard for extreme space weather, the storm that everyone references when they talk about worst-case scenarios. It happened in September of 1859, during a particularly active phase of the solar cycle. On September 1st, astronomers observed a massive solar flare, one of the first ever recorded by human eyes. Within hours, auroras were visible around the world as far south as the Caribbean. Telegraph systems, the cutting-edge technology of the time, went haywire. Operators reported receiving electric shocks from their equipment. Telegraph lines sparked. Some systems continued to operate even after being disconnected from their batteries. powered solely by the currents induced by the geomagnetic storm. The Carrington event was likely a G5 storm, the most extreme category. But here's the thing. Back in 1859, human infrastructure was minimal. Telegraph lines were the only technology significantly affected, and even then, the consequences were temporary disruptions and some equipment damage. Today, if a Carrington-level event struck Earth, the consequences would be far more severe because our infrastructure is far more extensive and far more interconnected. Satellite networks could be crippled. Power grids could experience widespread failures. GPS would be unreliable. Communication systems could go offline. That's why space weather scientists study the Carrington event so carefully, not because it's likely to repeat, but because it represents the upper boundary of what the Sun is capable of delivering. Now let's jump forward to 1989, March 13th. A severe geomagnetic storm struck Earth following a series of powerful solar eruptions. This was a G5 event, comparable in some ways to the Carrington storm, but occurring in a world with much more infrastructure at risk. The most dramatic impact occurred in Quebec, Canada. Geomagnetically induced currents overwhelmed the Hydro-Quebec power grid. A protective relay misinterpreted the situation and tripped offline. Within 90 seconds, the entire grid collapsed. Millions of people lost power. The blackout lasted 9 hours. Hospitals switched to backup generators. Heating systems shut down in the middle of a cold Canadian winter. Subways stopped. Traffic lights went dark. That event was a wake-up call. It demonstrated that geomagnetic storms were not just scientific curiosities. They had real-world consequences for modern infrastructure. In the aftermath, power companies around the world began implementing better monitoring, better modelling, and better protective systems. Grid operators learned to recognize the warning signs and take preventative action before currents reached damaging levels. The Quebec blackout was a painful lesson, but it drove improvements that make today's grids more resilient. Then there are the Halloween storms of 2003. Late October, early November, an exceptionally active sunspot region produced a series of powerful eruptions over several days. Multiple Ek-class flares, the most intense category, multiple coronal mass ejections, some of which arrived at Earth in rapid succession, creating exactly the kind of compounding effect we're discussing today, but at a far more intense level. This was a prolonged G4 to G5 storm environment. The effects were widespread. Satellites experienced anomalies. Some were temporarily disabled. At least one scientific satellite was permanently damaged. Airlines rerouted polar flights to avoid communication blackouts and elevated radiation exposure. Power grids experienced significant voltage swings, though operators managed to avoid large-scale blackouts by implementing the lessons learned from Quebec. GPS accuracy degraded, radio communications were disrupted, and auroras were visible as far south as Texas and Florida, a truly rare occurrence. The Halloween storms also provided an enormous amount of scientific data. Researchers studied the event extensively, using it to refine models of how CMEs interact with Earth's magnetosphere, how geomagnetically induced currents flow through ground networks, and how satellite systems respond to elevated radiation environments. That data improved forecasting capabilities and informed engineering decisions for future satellite designs and power grid upgrades. So here's the critical comparison. The Carrington event in 1859 was likely a G5 storm. The Quebec blackout in 1989 was triggered by a G5 storm. The Halloween storms in 2003 reached G5 levels. What we're experiencing today is a G2 storm, possibly briefly touching G3 conditions. The difference in intensity is substantial. A G2 storm is moderate. A G5 storm is extreme. The gap between those two categories is not linear. It's exponential. The energy involved, the effects produced, the risks posed, they scale up dramatically as you move up the G scale. This is why context matters so much. When you hear geomagnetic storm, your mind might jump to Quebec-style blackouts or Halloween storm satellite failures. But those were G5 events. What's happening today is multiple steps below that threshold. We're not in crisis territory. We're in routine monitoring with heightened ion territory. The professionals managing the affected systems are doing their jobs, applying protocols designed for exactly this kind of event, and ensuring that the public experiences no disruption. But let's also talk about why events like today's double CME impact are occurring in the first place. The Sun operates on an 11-year cycle, moving from periods of low activity, called solar minimum, to periods of high activity called solar maximum and back again. This cycle is driven by the Sun's internal magnetic field, which flips polarity roughly every 11 years. During solar minimum, the Sun's surface is relatively quiet. Sunspots are rare, solar flares and CMEs are infrequent. During solar maximum, the opposite is true. Active regions proliferate, eruptions happen regularly, and the probability of Earth-directed CMEs increases simply because there's more activity happening. We are currently in the rising phase towards solar maximum for solar cycle 25. Activity has been increasing over the past couple of years and is expected to peak sometime around 2025 or 2026, though predictions are imprecise. What this means practically is that we should expect more frequent solar storms over the next few years, more CMEs, more geomagnetic storms, more auroras for those at the right latitudes, and yes, more opportunities for unusual events like double impacts to occur. This is not cause for alarm, this is the natural rhythm of the Sun. Every 11 years we go through this. We've been through it many times, we'll go through it many times more. What's different now compared to past solar cycles is our level of preparedness. We have better satellites monitoring the Sun, we have better models predicting CME arrivals, we have better communication networks sharing forecasts with operators who need them. We have more resilient infrastructure designed with space weather in mind. We've learned from past events and applied those lessons. And here's something important to understand. The fact that we're seeing a double CME impact during this phase of the solar cycle is not surprising. It's actually expected that during solar maximum, when active regions are more numerous and more productive, the probability of multiple eruptions from the same region increases. What remains rare is the precise timing that brings both CMEs to Earth within the same narrow window. That's the low probability element. That's what makes this a black swan in the space weather sense. Not the occurrence of two eruptions, but the convergence of trajectories and timing that creates the double impact scenario. Looking ahead, we can anticipate more activity over the next 2 to 3 years. We'll see more M-class and X-class flares, we'll see more CMEs, we'll see more G1, G2, and occasionally G3 storms, and we might see another event like today's, where two CMEs from the same active region arrive in quick succession. Each of these events will be monitored, forecasted, and managed. Each will provide data that improves our understanding, and each will be an opportunity for those interested in space weather to watch science in action. But history also teaches us humility. We cannot predict with absolute certainty when the next truly extreme event will occur. We know it will happen eventually. The Sun is capable of producing another Carrington-level storm. The question is not if, but when. It could be next year. It could be 50 years from now. It could be 200 years from now. We don't know. What we do know is that the more we learn from events like today's, the better prepared we'll be when that extreme event eventually arrives. This is why scientists don't dismiss moderate storms as unimportant. Every storm, regardless of intensity, is a data point. Every unusual event, like a double CME impact, is a learning opportunity. The knowledge gained from studying today's storm will contribute to the models used to forecast tomorrow's storms, and the infrastructure improvements made in response to moderate events will provide resilience when severe events occur. So when you think about today's double solar strike, place it in this historical context. It's not the Carrington event, it's not the Quebec blackout, it's not the Halloween storms. It's a moderate storm with an unusual timing characteristic. It's noteworthy for its rarity and its scientific value, not for its danger. And it's happening at a time when we're better equipped to monitor, understand, and respond than at any point in human history. That's the story here. That's the perspective that prevents hype and focuses on reality. But perspective is only valuable if it leads to action, or in this case, informed observation. So let's talk about what you can actually do right now, what you can watch for, and how you can follow this event as it continues to unfold over the next day or two. Alright, so you understand what's happening, you know why it's scientifically interesting, you know it's not dangerous, but it's worth paying attention to. Now the question is, what can you actually do with this information? How can you follow along as this event continues to develop? What should you be watching for over the next 24 to 48 hours? And if you're in the right location, how do you maximize your chances of seeing auroras? Let's get practical. First, if you're in the northern tier of the United States, Canada, Scandinavia, or other high-latitude regions, You have a legitimate opportunity to see auroras tonight and possibly tomorrow night. The key factors are location, timing, and sky conditions. Location matters because auroras occur in an oval around the magnetic poles. During a G2 storm, that oval expands southward, making auroras visible at mid-latitudes. If you're in states like Montana, North Dakota, Minnesota, Wisconsin, Michigan, or even occasionally as far south as Iowa or northern Pennsylvania, you're in the zone. Timing matters because auroras are most visible during local nighttime hours, particularly after midnight when your location has rotated toward the night side of Earth. The magnetotail, the stretched-out part of Earth's magnetosphere on the side opposite the Sun, is where a lot of auroral activity gets energized. Being on the night side puts you in the best position to see the results. Sky conditions are simple. You need clear skies and minimal light pollution. Clouds will block your view. City lights will wash out the faint glow of auroras. If you can, get away from urban areas, drive out to a rural location, find a spot with a clear view of the northern horizon. Let your eyes adjust to the darkness for at least 10 to 15 minutes, and then watch. Auroras often start as a faint green glow low on the horizon. They might intensify into vertical rays or curtains that shift and ripple. They might pulse or flicker. Every auroral display is unique. If you want real-time information about auroral activity, there are several resources you can use. NOAA's Space Weather Prediction Center has a website with continuously updated data. They post alerts, forecasts, and real-time measurements from satellites and ground-based magnetometers. You can see the current KP index, which is a measure of geomagnetic activity. KP values range from 0 to 9. A KP of 5 or higher indicates storm-level conditions. During this event, KP is expected to reach 5 or 6, possibly briefly touching 7 if the second CME impact aligns favorably. Another excellent resource is spaceweather.com. They aggregate data from multiple sources and present it in a user-friendly format. They post images from solar observatories. They provide CME arrival forecasts. They share auroral photos submitted by viewers around the world. If you want a quick, accessible overview of what's happening, that's a great place to start. There are also mobile apps designed for aurora alerts. Apps like My Aurora Forecast or Aurora Alerts monitor geomagnetic activity and send notifications when auroral visibility is likely at your location. These apps use your GPS coordinates and current space weather conditions to estimate your chances of seeing auroras in real time. If you're serious about catching a glimpse, download one of these apps and enable notifications. Now, let's talk about the data itself and what it means. When you look at NOAA's real-time magnetometer readings, you're seeing measurements of Earth's magnetic field at various ground stations. During a geomagnetic storm, those readings show rapid fluctuations. The faster and larger the fluctuations, the stronger the storm. You'll also see the KP index updated every 3 hours. KP is a global average of geomagnetic activity. It's a simple number that summarizes complex data into an easy-to-understand scale. Another key metric is the BEES component of the interplanetary magnetic field. This is measured by satellites positioned upstream from Earth at the L1 point. BEES tells you the orientation of the magnetic field embedded in the solar wind that's hitting Earth. If BEES is negative, meaning the field is oriented southward, it couples efficiently with Earth's magnetic field, enhancing energy transfer and intensifying the storm. If BEES is positive, the coupling is weak and storm effects are muted. During this event, scientists are watching BEES closely as the second CME arrives, because the BEES orientation will largely determine how intense the compounding effect becomes. You don't need to be an expert to follow this data. You just need to know that negative BEES equals stronger storm, higher KP equals more activity, and larger magnetometer fluctuations equal more intense effects. It's pattern recognition. And if you spend even a little time watching these numbers during an active event, you'll start to understand how the system responds. Beyond tonight and tomorrow, there's another time window you should be aware of. AR 4324 is now rotating away from the Earth-facing side of the Sun. As it moves toward the far side, the window for Earth-directed eruptions from this region has closed for this rotation period. However, other active regions may develop as the solar cycle continues. This is not a prediction, it's a forecast of potential. Space weather scientists will be monitoring that region closely as it comes back into view. And if they see signs of renewed activity, they'll issue forecasts accordingly. This is how space weather works. It's not a one-time event. It's a continuous cycle of monitoring, forecasting, observing, and learning. The Sun is always active to some degree. Active regions come and go, some are quiet, some are productive, and occasionally conditions align in ways that create noteworthy events, like the double CME impact we're experiencing today. By following space weather, you're engaging with a scientific field that sits at the intersection of solar physics, magnetospheric dynamics, and practical technology management. You're learning to read the data that professionals use to make operational decisions. You're developing an awareness of the environment beyond Earth's atmosphere, the space environment that satellites navigate and that influences our technology in subtle but measurable ways. And here's why that matters. In a world where we're increasingly dependent on space-based systems, understanding space weather is becoming a form of scientific literacy. It's like understanding weather on Earth. You don't need a degree in meteorology to check the forecast and decide whether to bring an umbrella. Similarly, you don't need a degree in heliophysics to check space weather forecasts and understand whether auroras might be visible or whether GPS accuracy might be slightly degraded. This kind of knowledge empowers you. It removes mystery. It replaces vague anxiety with concrete understanding, and it allows you to appreciate the dynamic system we live within. Earth is not isolated. We orbit a star. That star influences our planet in countless ways, and increasingly, as we extend our presence into space, we need to understand and respect that influence. So over the next day or two, check the data, watch the KP index, look at magnetometer readings. If you're in the Aurora zone, go outside after midnight and look north. Take photos if you see anything, share them, engage with the community of people around the world who are watching the same event unfold. You're part of a global network of observers, connected by curiosity and enabled by technology that gives us unprecedented access to real-time information about our cosmic environment. And if this event sparks your interest, if you find yourself wanting to know more, keep following. Subscribe to channels that cover space weather. Follow scientists and forecasters on social media. Check NOAA's website regularly, because this is not the last solar storm you'll have the opportunity to witness. We're in an active phase of the solar cycle. More events are coming, and each one is an opportunity to learn, to observe, and to deepen your understanding of the Sun-Earth connection. But beyond just watching this particular event, beyond tracking auroras and checking KP indices, there's a bigger picture here that's worth considering. There are broader implications to why space weather matters, why events like this are more than just scientific curiosities, and why paying attention to the sun is becoming increasingly important for our technology-dependent civilization. That's where we need to go next, because understanding the immediate event is valuable. But understanding the larger context is what turns information into insight. Let's zoom out for a moment. Let's step back from the specific details of this double CME impact and talk about why space weather matters in a broader sense. Because this isn't just about one event. It's not just about auroras tonight or GPS accuracy tomorrow. It's about the relationship between our civilization and the star we orbit. It's about the vulnerabilities we've created through technological advancement and the resilience we're building to address those vulnerabilities. And it's about the profound realization that we live in a dynamic, interconnected solar system where what happens on the sun directly affects life on Earth. Start with this basic fact. In the span of just a few generations, human civilization has become fundamentally dependent on technologies that didn't exist a century ago. Satellites, GPS, global communication networks, interconnected power grids spanning continents. These systems enable modern life. They allow airplanes to navigate with precision. They allow power to flow from generation plants to homes and businesses. They allow you to check your phone and see information from anywhere in the world instantly. We built this infrastructure because it provides immense value. But we built it without fully understanding, at least initially, how vulnerable it is to space weather. Satellites are exposed to the space environment. There's no atmosphere to shield them. When a geomagnetic storm occurs, when energetic particles flood into regions where satellites orbit, those particles can damage electronics, degrade solar panels, and cause temporary or permanent malfunctions. Every satellite operator knows this. They design satellites with radiation shielding. They program fault-tolerant software. They plan for anomalies. But the risk is real and quantifiable. During severe storms, satellite losses increase, services degrade, and in extreme scenarios, critical satellites can be disabled. GPS is a utility we often take for granted. We use it for navigation, timing, surveying, even financial transactions that require precise time synchronization. But GPS signals pass through the ionosphere, and the ionosphere is directly affected by space weather. During storms, the ionosphere becomes turbulent and GPS accuracy suffers. For most applications, the degradation is minor, but for safety-critical systems, aviation, autonomous vehicles, precision agriculture, even minor degradation requires backup systems or alternative methods. Power grids, particularly at high latitudes, are vulnerable to geomagnetically induced currents during storms. The Quebec blackout in 1989 proved that. Since then, grids have been hardened. Monitoring has improved. Operators have better tools and better training, but the vulnerability remains. A sufficiently strong storm, particularly if it strikes a grid already under stress from high demand or maintenance issues, could cause cascading failures. It's a low-probability, high-consequence scenario that keeps power engineers awake at night. These are not hypothetical risks. They're documented, quantified, and actively managed, and they're growing more significant as our infrastructure expands and our dependence deepens. Every year, more satellites launch. Every year, more systems rely on GPS. Every year, power grids interconnect more extensively to improve efficiency and resilience against terrestrial threats. All of that makes us more capable and more vulnerable simultaneously. This is why space weather science matters. This is why events like today's double CME impact are worth studying carefully. Every storm teaches us something. Every unusual event provides data that wasn't available before. Scientists use that data to refine models, improve predictions, and develop better forecasting tools. Engineers use that data to design more resilient satellites, more robust power systems, and more fault-tolerant communication networks. Policymakers use that data to understand risks and allocate resources for mitigation efforts. And here's the remarkable part. We're getting better at this. Forecasting space weather has improved dramatically over the past 2 decades. Satellites positioned at strategic points in space provide early warning. Models run on supercomputers predict CME arrival times with increasing accuracy. Operational protocols ensure that satellite operators, grid managers, and airlines have the information they need to make informed decisions. We're not helpless in the face of solar storms. We're actively managing the risk. But there's also a sense of wonder here that's worth acknowledging. The fact that we can monitor the sun, detect eruptions as they happen, track coronal mass ejections as they travel through space, predict their arrival at Earth, and measure the resulting effects on our planet's magnetic field, all of that is an extraordinary achievement. We're observing processes that occur on scales of millions of miles and energies that dwarf anything humans can produce. We're watching a star influence a planet in real time, and we're doing it not with mysticism or superstition, but with instruments, data, and scientific understanding. Think about what that means. 100 years ago, people saw auroras and wondered what caused them. They had theories, but no direct observations. 50 years ago, we were just beginning to send satellites into space and realized that space wasn't empty and benign. It was filled with radiation, particles, and dynamic magnetic fields. Today, we have fleets of satellites monitoring the sun and the space environment continuously. We have real-time data streams. We have forecasts issued days in advance. We have systems designed to respond automatically when conditions warrant. This is human progress. This is science translating into practical capability. And it's happening in a field that most people never think about. Space weather doesn't make headlines unless something dramatic occurs, but it's always there, always being monitored, always influencing the technology we rely on, and the people working in this field, the scientists, engineers, and forecasters, they're quietly ensuring that our infrastructure remains functional, even when the sun throws challenges our way. Now, let's talk about the future. We're not done building infrastructure in space. Plans are underway for expanded satellite constellations, lunar bases, manned missions to Mars, space-based solar power, orbital manufacturing. All of these ventures will increase our exposure to the space environment and our need to understand and predict space weather. Astronauts traveling beyond Earth's magnetic field face radiation risks that must be carefully managed. Satellites in new orbits will encounter environments we haven't fully characterized. Lunar bases will need shielding and warning systems for solar storms. Space weather science will become more important, not less, as humanity expands into space. And the lessons we learn from events like today's double CME impact will inform the design of future systems. How do spacecraft shield against radiation? How do power systems handle induced currents? How do communication networks maintain connectivity during ionospheric disturbances? These are questions with practical answers, but the answers improve as our data and understanding improve. There's also a philosophical dimension here. For most of human history, we experienced space weather without understanding it. Auroras were interpreted as omens or divine signs. Variations in Earth's magnetic field went unnoticed. The sun was a distant, unchanging fixture in the sky. But now we know better. We know the sun is active. We know it influences Earth. We know we're part of a dynamic system, not isolated observers. That shift in perspective is profound. It connects us to the cosmos in a tangible way. When you see an aurora, you're not just watching a pretty light show. You're witnessing charged particles from the sun, particles that traveled millions of miles through the vacuum of space, being funneled along Earth's magnetic field lines into the atmosphere, where they collide with oxygen and nitrogen and emit light. You're seeing the Sun-Earth connection made visible. You're observing physics in action on a planetary scale. That's not mystical. That's not abstract. That's real, and it's happening right now. This is what makes space weather fascinating beyond the technical details. It's a reminder that Earth is not separate from the rest of the universe. We orbit a star. That star is active, and that activity reaches us. The light warms our planet. The solar wind shapes our magnetosphere. Coronal mass ejections disturb our magnetic field and create auroras. We're immersed in the sun's influence every moment of every day. Most of the time, we don't notice because the effects are subtle, or because our infrastructure handles them invisibly. But during events like today's double solar strike, the connection becomes obvious, and that's something worth appreciating. In a world where we spend so much time focused on screens, on artificial environments, on human-created systems, space weather reminds us that there are forces far larger than us, processes we don't control, phenomena we can only observe and respond to. It's humbling, it's awe-inspiring, and it's a call to curiosity. Because the more we learn about space weather, the more questions we uncover. How exactly do CMEs accelerate particles to such high energies? What triggers magnetic reconnection in the magnetotail? How do geomagnetically induced currents propagate through complex ground networks? These are active research questions with real-world implications. So when you think about today's event, when you consider the double CME impact and what it means, hold both perspectives simultaneously. Yes, it's a technical event with measurable effects on satellites, GPS, power grids, and auroras, but it's also a window into the fundamental relationship between our planet and our star. It's a demonstration of scientific progress. It's a reminder of our place in the solar system, and it's an invitation to pay attention, to learn, to engage with the universe beyond Earth's surface. That dual perspective, practical and philosophical, technical and wondrous, is what makes space weather such a compelling field, and it's what makes events like today worth your time and attention. But with all of that context, all of that history, all of those implications, we need to bring this full circle. We need to close out this discussion by recapping what we've covered, reinforcing the key points, and giving you clear next steps for staying engaged with this topic as it continues to evolve. So let's bring this together. Let's recap what we've covered, and make sure you walk away from this video with a clear understanding of what's happening, why it matters, and what you can do with this information. Because that's the goal here. Not to overwhelm you with data, not to scare you with worst-case scenarios, but to inform you accurately so you can appreciate the science and the spectacle of a double solar strike occurring right now. Yes, NOAA has confirmed that 2 coronal mass ejections are hitting Earth within a 24-hour window. The first arrived earlier today. The second is arriving within hours. Both eruptions originated from the same active region on the Sun, L43224, which has proven to be remarkably productive over the past several days. The timing of these impacts is what makes this event noteworthy. Not the intensity, which is moderate at G2 levels, but the rarity of having 2 significant strikes arrive so close together that the second hits before Earth's magnetosphere has fully recovered from the first. Yes, this creates compounding effects. The magnetosphere doesn't have time to relax between impacts. Particle populations that were injected by the first CME are still present when the second arrives. Currents that were initiated by the first disturbance are amplified by the second. The response is more complex and potentially more intense than a single impact would produce. This is the science that makes space weather researchers lean forward and pay close attention. It's a relatively rare scenario that provides valuable data for refining models and improving future forecasts. But no, this is not dangerous to you personally. Your life continues exactly as it did yesterday. Your technology works, your power stays on, your phone connects, your car starts. The effects of this storm are being managed by professionals who do this routinely. Satellite operators are monitoring their systems, power grid managers are watching voltage levels, airlines are adjusting routes if necessary, GPS users in high-precision applications are applying corrections, and for the rest of us, life is normal. The only people who might directly experience something unusual are those lucky enough to be in the Aurora zone with clear skies tonight. Now you understand what a geomagnetic storm actually is. You know that coronal mass ejections are clouds of plasma and magnetic fields ejected from the Sun. You know that when they reach Earth, they interact with our magnetosphere, compressing it, injecting particles, and driving currents that we measure as geomagnetic activity. You know that the G-scale from 1 to 5 categorizes storm intensity, and that today's G2 storm is moderate, not extreme. You know that the effects include satellite anomalies, GPS degradation, power grid voltage fluctuations, radio disruptions, and auroras, and you know that these effects are understood, anticipated, and managed. You also understand why double impacts are different. You know that timing matters because the magnetosphere needs recovery time between disturbances. You know that when two CMEs arrive in quick succession, the effects compound. And you know that this doesn't happen often, which is why scientists find it scientifically valuable. It's a black swan event in the space weather sense, a rare convergence of conditions that provides insights beyond what routine single-impact events teach us. You've seen the historical context. You know about the Carrington event in 1859, the Quebec blackout in 1989, the Halloween storms in 2003. You know that those were G5 events, far more intense than what we're experiencing today, and you know that we're currently in the rising phase towards solar maximum for solar cycle 25, which means we should expect more frequent solar activity over the next couple of years. This is not the last storm, it's one of many we'll see as the cycle progresses. You have practical information now. You know how to watch for auroras if you're in the right location. You know where to find real-time data, NOAA's Space Weather Prediction Center, spaceweather.com, mobile apps that provide aurora alerts. You know what the KP index means and why B's orientation matters. You have the tools to follow this event as it continues to unfold and to track future events when they occur, and you understand the broader implications. You know why space weather matters for our technology-dependent civilization. You know that satellites, GPS, power grids, and communication networks are all influenced by solar storms. You know that we're actively managing these risks through monitoring, forecasting, and resilient design. And you know that space weather science is advancing, that we're getting better at predictions, and that events like today contribute to that progress. So what do you do now? If you're in the Aurora zone, go outside tonight after midnight. Look north. Watch for that faint green glow on the horizon. If you see it, take photos. Share them. Engage with the global community of Aurora watchers who are looking at the same sky from different locations. If you're not in the Aurora zone, check the data anyway. Watch the KP index. Look at magnetometer readings. Learn to read the signals that tell the story of what's happening in the space environment above you, and stay engaged beyond tonight. This is not a one-time event. AR 4324 will rotate back into view in mid-January. If it's still active, we might see additional eruptions. Other active regions will develop as the solar cycle continues. More CMEs will launch. More storms will arrive. Each one is an opportunity to observe, to learn, to deepen your understanding. By following space weather, you're connecting with a scientific field that matters increasingly as our civilization expands into space and becomes more dependent on space-based infrastructure. If you found this video valuable, if you appreciate content that explains complex topics without hype or fear-mongering, hit that subscribe button right now. I'll continue covering space weather events as they develop. I'll provide analysis, context, and practical information so you stay informed without being alarmed. And I'll do it with the same approach we use today. Real science, real data, real explanations. Drop a comment below and tell me where you're watching from. Are you in the Aurora zone? Did you see anything last night? Or do you plan to watch tonight? Are you a satellite operator, a grid engineer, a pilot, someone whose job involves monitoring space weather? I want to hear from you. I want to know how far this information reaches and who finds it useful. This community is built on shared curiosity, and your engagement matters. Share this video with people who might find it interesting. Space weather doesn't get mainstream coverage unless something dramatic happens. Most people have no idea that events like today's double CME impact are occurring. By sharing, you're helping spread scientific literacy. You're helping people understand the dynamic environment we live in, and you're contributing to a culture that values knowledge over hype. Look, the universe is vast, dynamic, and endlessly fascinating. We live on a planet orbiting a star in a galaxy, containing hundreds of billions of other stars. Most of the time, we're focused on human concerns, daily routines, and immediate challenges, and that's fine, that's necessary. But occasionally it's worth stepping back and recognizing that we're part of something much larger. Space weather events are one of those opportunities. They're moments when the cosmos reaches out and touches us directly. They're reminders that Earth is not isolated, that the sun influences us constantly, and that we've developed the scientific understanding to observe and appreciate that influence. Today, 2 waves of solar material are striking Earth within hours of each other. It's rare, it's scientifically interesting, it's being managed competently by professionals around the world, and it's happening right now while you're going about your day. You're part of the story just by being aware of it. So stay curious, keep watching the sun. And remember, we live in a dynamic solar system where the star at the center doesn't just provide light and warmth, it actively shapes the space environment around us. Understanding that connection is part of understanding our place in the universe. Clear skies and keep watching the sun.